Thank you very much, and thank you to all the organizers for putting together this really nice meeting. It's a pleasure to be here, and I'm very happy to present a bit of my work. This is a joint project with Anne Termina, and you'll notice it's not that recent. It's actually ongoing work, so I can talk about it any time. And also, due to the pandemic, it turns out I've never given a talk about it. So this is it, at least after we had put it on the archive. Now, the setting here is the setting of... Not so old. I agree, and I remember, so that's the important part of it. Yeah. So the setting here is that of non-chiral superconformal field theories. In these non-chiral superconformal field theories, we consider special states, the so-called Bps states. And you should think of such superconformal field theories coming in families. So we're going to be interested in what happens to the spectrum, to the states, the space of states, when we deform the conformal field theory. And then it can happen that some of these states that I call quarter Bps cease being Bps. What's this with the Bps condition? Well, first of all, very, very vaguely in conformal field theory, you could say if it has a geometric interpretation, then a state with left and right conformal dimension could be viewed as something which is similar to a differential form with holomorphic and anti-holomorphic form degree. Much less vaguely, the Bps states correspond to differential forms which are harmonic. And for harmonic differential forms on a manifold, of course, we are used to using them to construct invariants because they are our favorite representatives of cohomology classes. And once we're talking cohomology, we can start counting Bps cohomology classes, or rather counting, so taking graded Z2 graded dimensions, and then we might end up constructing invariants. And that's actually why Bps states are so popular, because they can be used to construct invariants of conformal field theories. But of course, the states of Bps states themselves are not invariant. That's why we have to take Z2 graded dimensions in order to construct invariants. And it is, at least for me, an interesting question how a state can cease to be Bps under a deformation, or maybe become Bps later on under another deformation. So today's talk, of course, I will spend most of the time explaining what this quarter Bps condition is and how we can count Bps states, and then we will gradually zoom into examples where we can actually say something concrete. Those who know me will not be surprised that we will zoom into K3 theories, and then we will zoom in even more into Z2 orbifold conformal field theories of K3, because for those, actually, we have a prediction on how the process of seizing Bps is governed. In general, we'd like to have access to like a core space of states, which all K3 theories have. We pretty much know what that looks like, but then a standard K3 theory will have extra states, so I want to know how they arise, how they cease being in existence. So we first start counting Bps states. And I'll begin this subsection by saying what I want, and then I hope I can achieve what I want during the subsection. Namely, I would like to make sense of the following claim, which tells you how one counts Bps states in the context that I'm interested in here. So the claim is that the following does the job. Following counting Bps states. Actually, one word in the title wasn't addressed at all so far, the quarter thing here. And for starters, I'm going to work with half Bps states, and we'll see what that means in a few minutes. So the following is counting Bps states. That's the claim. And, well, it's going to be the conformal field theoretic elliptic genus, for those who know. Okay, so tau and z are going to be complex variables, as usual. They occur in the exponents, so we're going to build q is equal to e to the 2 pi I tau, where tau is actually in the upper half plane. And y is e to the 2 pi I z. And now I'm going to construct a trace over something. I have to say what something is going to be. Something is going to be a representation. In fact, a unitary representation for me of two copies of an n equal to super conformal algebra. So give names to them for later reference. So one copy will not have bars, the other one will have bars, and these are n equal to super conformal algebras at some central charge. At some central charge C. Not yet, later, yes. Later, yes, and in some way it's better if it's a multiple of 3 for what I'm going to require next. It's okay if you restrict your vision to multiples of 3, but I don't need it yet. Okay, so I mean, these have been on the board several times during this conference already. So let me put that here, AC n equal 2 is a super vertex operator algebra, and the generating fields are T and J and G plus and G minus. T and J are even. T, the Verasoro field, J, a current of a U1 current algebra, and G plus and G minus are giving us the n equal to 2 supersymmetries. So the modes of T are the familiar Ln, and C is the central charge, which I'm going to, of course, represent on H by just multiplication by some real number, and unitarity implies greater or equal than 0. Okay, and the Jn here, they form U1 current algebra, and for later purposes I need to tell you how everything is normalized, because otherwise some of the statements I'm making are completely void. So I'm normalizing things as follows. Here the central charge shows up, C third m delta m plus n. Okay, and now I can continue writing the formula that I want here, namely I'm going to put a -1 to the J0 minus J0 bar, where J0 already occurs there, and I'm going to assume that the spectrum of J0 and J0 bar is completely integral. Actually, I'm going to assume that J0 bar are simultaneously diagonalizable. And what else? The spectrum. I already said that. The eigenvalues are all going to be integers, so that the -1 to the J naught, etc. there is really no trouble. Okay, but the formula isn't done yet. So next, the y that I introduced already is going to show up. We're going to have y to the J0 minus C by 6. So we're a little happier if C is a multiple of 3 here, but we're not really scared of an expression like this. And then in addition, we will see L0 and J0 here, and Q bar to the L0 bar minus J0 bar divided by 2. Okay, that's the formula. And I'm going to make one more requirement here, actually split into 3 ingredients. L0 and L0 bar participate here in the simultaneously diagonalizable operators. And also I'm going to require that this thing here looks a little bit better. Namely, I'm going to require that the thing that looks like conformal spin now is also always integral. So I have those shifts in there. A little more work to write it out. But the difference between the exponent operators there on the left and right also is supposed to have only integral eigenvalues. Okay, so these are the requirements I'm making here, and I'm not writing it out in much more detail. I want to somehow make sense of this thing there, and it better have a chance to be well defined. So really, I'm also assuming that all the simultaneous eigenspaces are finite dimensional, etc. But I'm not going to write it down in that much detail, because later, when I assume that H comes from a superconformal field theory, all these things will be there by free. So I'm not going to spend too much time with this here. Okay. You'll see, because I want to count Bps states. It's a very, very short answer, and you'll see that that's exactly crucial, that it's a little lopsided. And thank you, I often make mistakes in the formula, so it could have been a mistake that I just forgot the other one, but here, actually, I knew what I was doing. Okay, so you'll see later, good question, you'll see later why that lopsidedness here is actually crucial. And I also have to tell you a little more about the normalizations here, because it's sometimes a little non-standard the way I do it. For me, L0 actually measures energy, and that's captured in the index here. So for all n, L0 will commute with xn to n xn, and that's the plus n here if x is either L or J. And J0 is going to measure what I call U1 charge. And for the even generators of this superconformal algebra here, that's just 0. And we also have the G's. And I'm taking the indices here as half integers. And again, L0 measures the index. And this will help us later on. And J0 measures the charge, and the plus minus here indicates that they have charge +1, respectively -1. And the fact that those are integers is, of course, crucial, and that's all sensible is hidden in the specific normalizations that I chose here. So for all purposes of this talk, you need to remember that things are normalized in a way so that life becomes a little easier. Okay, and the fact that I'm saying unitary there, of course, again, I'm not going to write out all the requirements, but one important one, which is then indicated, is the fact that this scalar product is actually positive definite. And the other requirement that implies is that we know what the adjoints of all these operators are. So the adjoint of one of these even guys is obtained by just flipping the sign of the index here. And similarly for the odd guys, just that also the charge changes. Okay, and that's going to be helpful later on. So that's the statement, but still not all the words have been explained. In particular, this word BPS hasn't been explained. So let us recall what BPS is, or learn what BPS is, depending on which area you come from. BPS is shorthand for Bogomolny and Prasad and Sommerfeld. There were 2 papers in the mid-70s where essentially in parallel the same ideas were discovered, namely Bogomolny on one hand and Prasad and Sommerfeld on the other hand, observed that in this situation there we have a couple of inequalities that are always met. And these inequalities should remind you of your childhood days when you were calculating the Ram cohomology, because things are similar to the setting there. And that's exactly why I said at the beginning BPS is similar to being harmonic. Okay, big words, simple calculation. What you should do is consider any element of our space H. And because we have a positive definite scalar product, when I consider the length square of, say, the thing that I get when I act on V with G plus 1/2, put it twice into the scalar product, that's going to give you a non-negative number. And because we already know that the adjoint is what it is, I can pull G plus to the other side. Okay, but now, of course, I didn't write out all the commutator, anti-commutator relations that we have in the n equal to superconformal algebra. And the one that I would like to use now is the one that tells me what the super bracket on these 2 guys is. So let's recall what it is. Well, if you really want to use super brackets, we take the square bracket all the time. And what you actually get is quite easy. It's 2L0 minus J0. And here's a mistake. I'm sorry. The plus, because that's, well, part of what we see over there. It's only half of what we see over there. Let's fix it and add the other half. And then there, I can play the same game with using the fact that I know what the adjoint is. Go. Okay, and the fact that it's non-negative is even more so true if I add two non-negative numbers. And now you see that exactly that operator over there is emerging. That's 2L0 minus J0. And I've just proved to you that this is a positive semi-definite operator. And we also know when exactly we have equality here. Namely, if and only if both these ingredients here vanish and both these ingredients vanish if and only if these vectors here vanish. So if and only if G plus 1/2 is killing V, as is G minus 1/2. And these are the states that we are particularly interested in. These are the elements of H that we are particularly interested in. These are called Bps states. Definition. V and H Bps. If L0 to L0 minus J0 tends V to 0. Well, I've just been working on the holomorphic side now. We have two n equal to 2 super conformal algebras to play with, so there's also an anti-holomorphic side. And really, I would call V Bps only if this condition held, both for the guys with a bar and without a bar. I want to focus on those that are half Bps at this point. And I'm going to throw out the holomorphic dependence. So instead of the calculation I showed you, I'm going to use the with the bar. And these are called half Bps. Why half Bps? Well, naively, because I'm only using half of the conditions that I could be using better. Well, look, if V is non-zero, and if we accept that G plus 1/2 is actually a supersymmetry here, G plus 1/2 would produce a superpartner for V. But if that superpartner vanishes, there is no superpartner. So if we're considering a Bps state, actually part of the supersymmetry broken. Or partially broken. And just imposing half of the conditions that we would have, we're essentially just using half of the supersymmetries that we're interested in. And so here, half of the supersymmetry is broken. And that's why I'm saying half Bps states. And you can see that later on I'm going to reduce further. At the moment, we cannot see how that would make sense. But at the moment, we're going to have quarter Bps states, and it will be very natural why we move from half to quarter. OK. So that's that. That's the formulation of the claim. And why am I claiming that we're actually counting these states? Well, one thing that's maybe worth noticing is when we consider what J0 does, it measures charge. And well, actually, G plus and G minus have odd charge. So they change the parity of the charge when we act with them in any state, while the even states don't do that. And it makes sense to view the -1 to the J0 minus J0 bar as the thing that implements your Z2 grading on the space H. And that's what's happening when all this shows up in superconformal field theories. So actually, it's OK with all this as just the supertrace. But it's more concrete the way I wrote it. And it's just words. But that's actually the supertrace that you might be used to when constructing indices in geometry. OK, but again, what about the counting? Well, note, we're going to consider eigenvectors of our new favorite operator here. So let's assume that V is now a non-zero element of H. And actually an eigenvector of this guy up there. And I want to assume that lambda is greater than 0. And I want to consider the superpartner of this guy with the terminology that I just used a few minutes before. then I'm claiming that G1/2 plus applied to V, and don't forget the bar, is also an eigenvector of that very same operator. Now, why is that so? I can simply pull the operator past this guy. Of course, I have to remember the rules of the game here. L0 bar measures the index. So L0 bar is either 1/2 isn't multiplied by 2. J0 bar measures the charge. That's +1 here. Subtract +1 from +1, get 0. So this guy actually does commute with this one here, and that means that we have found another eigenvector with the same eigenvalue. And now we're looking in the definition here of this guy. So with that calculation, we see that these two vectors, which are certainly linearly independent, these two vectors contribute with the same values to this thing back here, and we can arrange it by using this simultaneous diagonalizability criterion. We can arrange that, of course, this one is also the same. Well, that means that the contributions of these two states to the counting here, to the trace here, to the supertrace cancel out because they have different parity, because we factored here. So these contributions cancel out, and altogether, that E here reduces to something much easier. Namely, it reduces to the supertrace. Now, not taken over all of H, but taken over the kernel of my favorite operator. And those are the half Bps. I sometimes call this space curly H half Bps states. And now back to your question. I cannot play the same game with the unbarred guys because Y is in the way. Because Y will in general distinguish between these two guys. They have different. So that's why I don't want a Y bar in there. If I also get rid of Y, then I produce a constant, but that's not what I want to do here. So that's why we have the lopsidedness here, and including the Y, I get, a little bit of a handle over this potentially rather thing. And even better, well, we can now see that we've produced something that has a nice interpretation as formal power series as well, up to maybe some prefactor, and it's the formal power series in y to the -1, because I required that J0 only has integral eigenvalues, and in Q, because I have also a requirement on the spectrum of L0 minus J0 ½ It's right here. I've forced this guy here in curly H to have eigenvalue 0, so the condition that I'm writing out there means this guy only has integral eigenvalues. So there we are. And there we are with something that under deformations of H cannot change, because we have integral coefficients, we have integral exponents, so we have produced an invariant. Counting, well, as you see, counting. Well, I said it already here. As you see, counting half Bps. Maybe at this point, it's useful to say a few words about how we think of deformations here. So at least in all the applications I have in mind, when we make a deformation of the space H, actually the vector space itself isn't deformed, but the representation is being deformed. So in particular, I could follow one of these eigenvectors through the deformation, and the vector would remain an eigenvector, but the eigenvalue would change. And when I say invariant, I mean under what we would call continuous deformations. And then these eigenvalues, like the lambda up there, these eigenvalues would deform or would change continuously. And it is possible that one of these eigenvalues, from being non-zero, somewhere along the way becomes 0. So it is thinkable that maybe, or you can imagine, that maybe some Bps states cease to be Bps. But from the fact that we have an invariant constructed like here, we already know that that can't happen just out of the blue. This can only happen in pairs because the contributions to E of the things that are actually ceasing to be BPS or starting to BPS, they have to cancel out because E cannot change. So we can only have BPS states cease being BPS in pairs, in boson fermion pairs, and conversely, if something arises anew, it also has to happen in boson fermion pairs. And that requires the observation that actually curly H is not an invariant. I already spoke about deforming things. I already spoke about states being BPS and ceasing to be BPS, and that only makes sense if this is not an invariant. And we have tons of examples where we can see that very explicitly, and I'm going to get to one of those in a bit. Okay. Well, I'm having in mind concrete examples of theories with geometric interpretation, and then so that's something that's at least related to a nonlinear sigma model construction, and then you're varying the geometric data. And it will become a little more specific later when I'm actually zooming into the examples that I want. And there's a formal way of defining the deformation theory. I don't want to go into that too much. I will use that later in hiding for these n equal to 2 super conformal field theories, which H will be part of the space of states of later on. The deformations are actually governed by BPS states, by full BPS states, so left and right BPS of a certain conformal weight, and we'll see for the K3 theories which they are. So then you don't need the geometric interpretation to state what a deformation is, and those are sort of built into the theory that the deformation theory, we see the tangent spaces to the moduli spaces inside the theories here. Okay, good. That was part 1. Very good. Four. I didn't say that was a quarter. I have another blackboard here. Okay. Oh yeah, so let's start counting BPS states in K3 theories. What's the K3 theory? Well, it's an n equal to super conformal field theory. At central charge 6. Now we have a multiple of 3 at C equal to 6, where in addition, I'm requiring 2 things. First of all, space-time supersymmetry. So for those who know, this is related to the spectral flows that we've seen all about during this conference already. For those who don't know, don't worry too much. In particular, this assumption here implies all the assumptions that are made on the spectra over there. So now they come for free. And also saying superconformal field theory implies that that counting function that I used over there is actually well defined. So I'm home free now, and that's why I didn't put more details in there, because I won't need them. And secondly, if I now for H use the Neveu-Schwarz sector of this theory, and for those who don't know, this is just sort of half of the space of states of your superconformal field theory. And one can do all the work on this space because we have required space-time SUSY. And now H is given as the Neveu-Schwarz sector of such a theory. I can insert it over there, obtain a function E, the complex elliptic genus, the conformal field theoretic elliptic genus of this theory. And I want to require that it's non-trivial. And that's all I need to say without justifying why I call it K3. We'll see that in a minute in a comment. Okay, maybe now is the time to wipe the board. What do you mean happens? Well, you can write everything out in the Ramond sector. I'm actually in hiding spectral flowing here to the Ramond sector and using the partition function of the sector. Just the Ramond sector is completely obtained from the Neveu-Schwarz sector, so I use spectral flow and construct everything there. So you can formulate also the whole BPS stuff in terms of the Ramond sector. Yes, absolutely. There's too many words already anyway, so not going into that. Okay, but what do we have as a consequence of requiring K3 theories? Well, the most important consequence is that supersymmetry gets extended automatically because of the fact that we have those spectral flow operators in the game. They actually extend our superconformal algebra. Spectral flow operators arising because we have space-time supersymmetry. So for K3 theories, we have the following convenient situation. These two guys, the superconformal algebras that we have already been using, are automatically, secretly extended to n equal to 4 superconformal algebras. So now we are studying n equal to 4, 4 superconformal field series, and for them actually we can show along the lines that I said in answer to David's questions. For these theories we can show that they actually depend on 80 parameters, so there's an 80-dimensional deformation space here. And as such, so as n equal 4 for superconformal field theories, they depend on 80 parameters. So that number won't bother us anymore in this talk, but just to have some number, it's plenty of room. Okay, and now with these n equal to 4 superconformal algebras, one can start considering irreducible representations, and those are classified. At the moment, I'm just looking at the chiral part, yes, and later I'll put it together again. I don't know whether I have time for it, but that is the plan. I will put it together again, and at the moment, I'm just looking at the irreducible representations, all of which are lowest weight representations, so you should think of a Fock space representation, and it all depends on whether your lowest weight state is actually BPS or not. If the lowest weight if the lowest weight state is BPS. Yeah. I'm looking at the unitary case. Yeah, exactly. They're all lowest weight representations. If the lowest weight state is BPS, then you get a so-called short representation. No surprise, because I'm thinking of the representation as arising as a Fock space representation, so I'm acting with all those monomials built from the generators over there, and I'm introducing an extra zero here by saying that my lowest weight state is BPS, so it vanishes under G plus bar 1/2. So there is an extra zero. These are the so-called short representations. And they're either of weight, lowest weight state is either of weight h equal to 0 or of weight h equal to 1/2. And nothing else is possible. So that's tied to the fact that I assumed central charge 6 here. If not BPS, then you have long representations. And you can have any conformal weight h greater than 0 for the lowest weight state. Over here, I said BPS, so I also told you what the charge of the lowest weight state is. Here, it's always double of the weight. So here it's 0, and here it's 1. Down here, it's non-BPS, so I have to tell you what the charge is. Actually, it's 0, so uncharged. And again, I mean, colloquially, it's clear that this is a longer representation because you don't have these additional null vectors. But very concretely, what one can do now is investigate what happens if you perform a deformation where you send h to 0. When h hits 0, we're in this BPS situation here. When h hits 0, actually the long representations split into 3 short ones. One of h equal to 0, one with h equal to 1/2, and another one with h equal to 1/2. So 3 BPS representations arise from one long, 3 short BPS representations arise from one long BPS, from one long non-BPS representation. And we have to make sure that states can cancel out in pairs because we have this invariant E somewhere hiding there. And they do cancel out in pairs. Well, these two are fermionic, the ground states, because the charge of the ground state is 1, an odd integer, and we're using the Z2 grading that comes from the U1 charge. Here the ground state is a boson, so the ground state can cancel one of these, and there's a second one in here at higher level, which is also BPS and can cancel the other one. So this can be checked explicitly. And this is the procedure we're expecting here, or this is just happening here. We know it's happening when we deform these superconformal field theories. It will happen that such long representations split up into short ones. And in real life, the situation is actually the opposite, that you're starting with theories which are hardly more symmetric than the generic theory. So you have a lot more BPS states than you would need to, and you perform a deformation and then observe BPS states ceasing to be BPS. And yeah, that's actually what the title of the talk alludes to. Why quarter BPS states? I still didn't explain, but I did in hiding because I told you that the supersymmetry is now extended to n equal to 4. And I'm going to change exactly nothing in my definition of whom I want to consider, which states I want to look at. I want to look at the states that obey the equation L0 minus G0 half acting on the state 0. That's with a bar. So that's the equation I want. It now kills just a quarter of the supersymmetry because we have more supersymmetries. This is just one of them. That's why now what was half before is quarter. Now, I don't actually in real life use these words too often because they're confusing and they kind of depend on what the context is. So anyway, I told you which states I want to consider. Good. Making up for I missed. Oh, one thing more I wanted to say. I wanted to justify why we call these theories K3 theories. Actually, now you have put enough restrictions on the whole story to actually calculate this function E in this setting. And it turns out that it is just the complex of the genus of a K3 surface. That's the name, K3. Okay. Now, the sad truth is that although we know that we're living in an 80-parameter space, we don't know how to calculate many of these theories explicitly. We do have access to a whole bunch of examples, namely orbifold conformal field theories, and the ones that are particularly well under control are those theories that are easiest orbifolds. So the Z2 orbifold conformal field theories are actually well under control. And we can start looking at this space curly H for those theories and try to count quarter BPS states. Okay, so let's do this for Z2 orbifold. Say again? What do you mean moduli space? Well, you would have to distinguish. That's the problem. That's why I'm not answering, because it's not going to help. Because if you say K3, you have to tell me, do you want to consider complex vectors on K3? Do you want to consider Einstein metrics on K3? Do you want to consider hyperkähler structures on K3? So all these give different answers, and all these enter into the 80 parameters there. So not all of the 80 parameters are geometric, because you can construct a B field as well and insert extra parameters. And that's why I'm calling not to answer your question, because it's going to confuse us more. But yes. Great. But yes, the 80 is related to the K3 moduli, but not in a very, very, very direct way. So we can talk about it afterwards. I can decompose the 80 into, you know, solely geometric stuff and not so geometric stuff. Okay? Good. I was about to turn to Z2 orbifold field space. So 3 days ago, this talk had about 3 times the amount of material. I was planning to actually write out all the gory details of what the Z2 orbifold conformal field theories on K3 give us here. It's good that I don't have that much time because that also would have been way too many words. So what we're now going to do is just very roughly try to understand what the content of the space curly H is for this particular example. So what I really want to understand is the space curly H. That was the kernel of L0 bar minus J0 bar divided by 2. And saying orbifold conformal field theory, I think all of you know that this means that these theories come in 2 sectors, twisted and untwisted sector. Okay, so we will have ingredients from the untwisted sector, which are potentially easier to handle, and from the twisted sector. And I should be discussing, well, on the one hand, the behavior under the spiral n equal to 4 superconformal algebra, and on the other hand, under the anti-chiral or non-chiral, I don't know how you say it, right moving, n equal to 4 superconformal algebra. Say again? Simple. I don't think so. I don't think so. I don't think so, but I don't know. I don't know from the top of my head. I don't think so, not in general. Maybe the C equals 6 ones are. What was that? They have to be? Because? That is true. That is true. Okay, yes, thank you. They're simple. Good, and I'm going to try and put content into these boxes here. On the right-hand side, under the barred guy here, I already told you everything because I said BPS. I'm requiring BPS, and I told you up there are 2 choices for BPS. One is h bar equal to 0. One is h bar equal to 1/2. This one is uncharged. This one has charge 1 if I focus on the ground state. So I'll do that anyway. Focus on the ground state. And on the right-hand side, there's anyway just the BPS state. It turns out that in the twisted sector, you cannot have h bar equal to 0. So here we have h bar equal to 1/2 from the start. And I can say a little bit more about the structure here because I said Z2 orbifold conformal field theory. So what governs this is actually an underlying lattice VOA, which you all understand very well. In particular, we have external fermions. Use these external Dirac fermions. 2 of them on each side of each charge. I'm denoting them by chi's. K corresponds to the coordinates of the underlying complex torus, plus and minus corresponds to the U1 charge, and having a bar or not corresponds to being on the left or on the right. And then, of course, for h equal to 0, you have the vacuum in that representation. For h equal to 1/2, you see immediately how to construct something. You have just these guys. 2 of those. So there are 2 of these representations, definitely. And on the twisted side, one checks that there's a 16-dimensional space of twisted ground states. So these are built on some alpha in a 16-dimensional space of twisted ground states. how can we combine this with something on the left so it makes sense? Here I have all the freedom that I gave you up there. I could either combine with a BPS representation or a non-BPS representation. However, if I combine with a BPS representation, I'm actually producing half BPS states. I want to consider quarter BPS states, so I'm actually ignoring the which are not half. I'm ignoring the half ones. Not half, but quarter BPS only. Why? Well, because I don't have enough time to also go into the half BPS states. It's actually quite rewarding to do that. It's a nice little exercise because you can recover some of the data that you are familiar with from K3 surfaces maybe, etc. But the point is that the half BPS states, they don't ever cease being half BPS in this situation. So there's nothing happening under deformations for those states that obey two of these BPS conditions, one on the right and one on the left. So for this talk, I want to leave them out of the picture. I'm just ignoring them. Not that they're not interesting in general, they're just not interesting for the questions that I'm asking here. So instead, if I don't want BPS on the left, then there's no choice anymore. There's just the non-BPS thing there, the long representation. So all of these look the same on the left, long non-BPS representation with ground state at some positive weight uncharged. Well, not just any positive weight, because I have these requirements on the spectrum, which I haven't erased. I haven't erased them. Again, we're in this situation where on the right-hand side, this altogether gives 0. Also J0, 0 on the ground state, because I told you it's uncharged. So L0 better have only integral eigenvalues. So H is actually an integer here. Positive integer. And if we're interested in BPS states ceasing to be BPS, and we have in mind that because all of these invariants that I discussed, this can only happen in pairs, in boson-fermion pairs, I should remark that we know who's a boson and who's a fermion here, the ground state. Who's a boson and who's a fermion? Well, on the right here, we have charge 0. On the left, we have charge 0. So this first one is bosonic. I call it type A. This second one here is fermionic, because on the right we have charge 1. On the left, for the ground state, we have charge 0. So this one is fermionic. These ones, 2 on the right, infinitely many on the left. And the last one is also fermionic for the same reason. So we know a priori, if we can find states that under some weird deformation cease to be BPS, we know that we have to take something of type A and combine it with something of type B or type C, and then they team up, they pair up to long representations. So that's what's going to happen. So deformations, I was already asked to be more specific about that, and it's easier in this context where I can allude to the geometric content of the theory. In particular, we can, of course, deform those Z2 orbifold conformal field theories by just deforming the underlying toroidal theory. And that amounts to just deforming the lattice, the defining lattice on the underlying torus, and maybe a little bit of more information. And already on that level, you can see this effect happening, that sometimes quarter BPS states cease being BPS. Well, what does it mean to be in one of these, say, type A of what I listed here for a toroidal theory? Picked out all the half BPS states. So what it means is that on the right-hand side, for the bosonic, the underlying bosonic lattice vertex algebra, you have a contribution of h bar equal to 0, by the way. You have h bar equal to 0, so you have some additional chiral states in your conformal field theory. And that can happen only at special values of your underlying torus lattice. And as the lattice gets deformed away from this special location, say, you can see that the bosonic contribution to your state actually picks up some anti-holomorphic weight, but no charge. So you kill the BPS condition because you always have to pay by charge. If you want to keep this condition that L0 bar is equal to J0 bar half, you cannot just increase the eigenvalue of J0 bar. You also have to take J0 bar along. And what happens then is that, of course, untwisted states combine to longer representations. So what you see very explicitly happening in that situation is that states of type A pair up with states of type B and form together out of the short representations that they used to form a long representation, and they cease being BPS. So that's actually, I think, reasonably useful for illustration, but it's not new and it's not particularly interesting in terms of studying this behavior under deformations. What's more important is that also we can discuss deformations away from the Z2 orbifold conformal field theories. And the big question is which of these states here cease to be BPS and under which conditions and who pairs up with whom. And that's a mess. It's difficult to answer this question because we don't know how to construct these theories if they're non-Z2 orbifolds. And also the deformation theory is a bit complicated. But what we do know, and that's maybe surprising, what we do know is that under generic deformations, all the states of type A cease to be BPS. So we know that actually I pointed out a couple of years ago, and this uses crucially very beautiful work by Balin Song. I'm putting the publication date here. It was on the archive, of course, also in 2017. What is known is that all states, all quarter BPS states, of type A cease being BPS under deformations away from the Z2 orbifold. And the question is, whom do they pair up with? We always have leftover states, even if we take a generic torus lattice. We have leftover states of type B, we have states in type C, and the question is, who do they pair up with? And that's something that Anne and I have been trying to investigate in this project. That is the topic of this talk. And I have 5 minutes? Okay, 5 minutes for the fourth part of this talk, which is trying to say that we have a natural SU2 action governing the pairing up of states from short to long representations, if we are considering a very, very special deformation. All this is, of course, crucially dependent on the deformation that we're considering. Who pairs up with whom and whether states cease to be BPS depends on the type of deformation. And so I have to choose a direction of deformation. And I already briefly mentioned that each of the BPS states here, actually those with h bar equal to h equal to 1/2, each of these corresponds to a 4-parameter space of deformation. And so I can formulate things in terms of the states, the BPS states, now the half BPS states, half of which I've listed here, in order to say which deformations we're using. And the point is that if we're using deformations coming from this lower part here, from the twisted part, then we are leaving the Z2 orbifold conformal field theories. So those are the deformations we should be looking at here. And the maybe not so surprising news is that if we do that democratically in all the 16 directions of this 16-dimensional space after a suitable choice of basis, then we will support as much symmetry as possible, and life will be a little bit easier. And I don't want to write the technical details. I'm just going to say we're using alpha diagonal. This is kind of a diagonal sum over a choice of twisted ground states up there. And it does what I said. It deforms in each direction democratically and at same speed. And well, now, actually, I should say that there is very beautiful work on second-order deformation theory in this setting here by Christoph Keller and Ida Zadeh. This is in 2019. And they, among other things, show that as long as we're deforming in this, into this twisted sector direction, this here is actually true already to second-order deformation theory. One can see this happening. So they, just for the general picture, prove that it doesn't matter in which twisted direction you deform, but if you choose the one that we are using here, if you choose the one here, then you find a lot of states that do not cease being BPS. All states of type C, which are perpendicular to where the ground states are perpendicular to this guy, built on ground state in the orthogonal complement of this guy here, remain BPS, quarter BPS. And I denote them by C perp, obvious reasons. So our choices are now limited. I know I have to find partners for everybody in A, because everybody in A, they're all bosonic. All these guys cease to be quarter BPS, and they have to pair up with someone of type B or someone of type C, but not perpendicular there. And here's where we have a proposal where we claim that our SU2 symmetry actually governs the situation. And I'm saying it's natural, it's really very natural. The way this symmetry arises is not surprising at all, but the fact that we can make use of it is hopefully a little bit surprising, because it all goes back to the fact that we're starting with a Z2 orbifold conformal field theory on some torus C2 divided by lambda. C2 is R4, so we have on C2 at least an action of SO4. It's not a symmetry of our torus and not a symmetry of our torus theory, but locally you get symmetries from this. And indeed, in all the Z2 orbifold conformal field theories on K3, you have two copies of SU2 surviving the orbifolding, and they stem from the original SO4 in here. And the first one of those is well known. The first one of those actually is part of our n equal to 4 superconformal algebra. So this one was used in hiding all the time already. If you want to see how the action goes, maybe the best way to paraphrase this is to say that those Dirac fermions there are actually forming doublets. And the notation is not too pretty to get. Okay, so this one is old and well known, but not too obviously geometric. The other one is has a much more obvious geometric origin. It's namely the SU2 that you naturally have acting on C2. Again, I'm not claiming that this is a global symmetry. It can't be. It's not even a symmetry of the torus, but the local symmetry here does survive. So this SU2 is actually present in all orbifold conformal field theories, Z2 orbifold conformal field theories. On K3. And also, kind of paraphrasing a little bit, what it does is that now the doublets look much prettier. You just you think of these as differential forms, dz1 and dz2, if you want. where Z1 and Z2 are the complex coordinates on C2. And well, this comes from a geometric SU2 action, which SU2 we're not expecting to act on our conformal field theory, on the space of states of our conformal field theory, and one can now find, so that's what we actually did here. We find that SU2, the geometric SU2, which I'm alluding to over there, acts naturally if we restrict the space of states, our attention to that part of the space of states which is still in the game for this BPS discussion. So this acts naturally on, well, who is still in the game, A, B, and the diagonal part of C is still in the game. And by considering the local properties here, we come to the conjecture that the cancelling of BPS states, quarter BPS states, can only happen in accord with this action so cancellation is a word I didn't use in this talk, but we use in the paper. So that's the pairing up of BPS states to long representations, so ceasing to be BPS. Cancellation of quarter BPS states can only occur between states that transform in isomorphic representations of this SU2. Irreps of C2 geometric. In particular, at low level, we know that this is true because we can just calculate it by hand. Actually, at conformal weight h equal to 1, one finds that A just reduces to a 3 plus 3 bar of this SU2 geometric. B is actually trivial, and C diagonal reduces to a 3 plus 3 bar as well. And because we need to pair someone from here with someone from here or here, the statement is trivial at h equal to 1 because you don't have other choices. So there it's definitely correct, but at higher level we can check this by direct calculation. We have no proof of it, but it's terribly, I list a number of more pieces of evidence, but we don't have time and we do have hunger. But one more thing I want to say is that this also implies that the cancellation only happens between states in A and states in this part here, because very simply, we can calculate the irreducible representations entering in each of these. And all of those in A have odd dimension. All of these in B have even dimension. All of those in C have odd dimension. So if the conjecture is true, B is out. And saying it positively, these never cease to be BPS. So again, we have access to a little bigger space of states that is not BPS. All right, so I think 2 minutes before lunch, so thank you for your patience, and I am good.